Okay, dear students, today we will solve example 5.2 from the book McConkey and T.D. So here is the hot reservoir at 800 centigrade. So we have taken that 800 centigrade and we have converted into Kelvin, that is 1073 Kelvin. And a cool reservoir, that is 15 centigrade, are available. Okay, calculate the thermal efficiency and the work ratio of the Carnot cycle. So you have to find the thermal efficiency and the work ratio of the Carnot cycle using air as the working fluid, and the maximum and minimum pressure in the cycle are 210 bar and 1 bar. So maximum pressures are given, and higher temperature and lower temperature of the systems are also given. Remember, before starting this example 5.2, you must be familiar from the Carnot cycle. The Carnot cycle TS diagram is just like this, as a square type shape, you can say. So it have four processes. 1 to 2 is isothermal isentropic expansion, so it's isentropic expansion. Okay, then 2 to 3 is isothermal, because here is temperature response is isothermal compression. Okay, and then 3 to 4 is isentropic compression. So after 2 compression we got a maximum pressure, that is 210 bar at state point 4, and after 2 expansion, this is isothermal expansion. So here is the isothermal expansion. So in isothermal expansion we have heat addition process occur. So after 2 expansion, we got the lower pressure, that is 1 bar. Okay, so we have now understand the TS diagram of the Carnot cycle, because the whole example 5.2 move around the Carnot cycle. So we have temperature T1, and that is 800 centigrade. When you convert into Kelvin, it becomes 1073 Kelvin. And T2, that is lower temperature, that is 15 centigrade. There's a 273 with 8 to convert into Kelvin, so it will be 288 Kelvin. Next we have to find the efficiency, Carnot efficiency we have to find, and then the work ratio. Okay, so finding the Carnot cycle efficiency is very easy, but you have to do lots of works calculations in order to find the work ratio. So a simple Carnot cycle is 1 minus T2 divided by T1. Okay, so 1 minus T2. So what is T2? T2 is the lower temperature, that is 288, divided by higher temperature is 1073. Okay, just do that in calculator. Divided by 1073, you will got 0.73. If you multiply it with the 100, it will give you 73.2% almost. So this is the efficiency of this example 5.2. Now we will find the work ratio. For work ratio, it is necessary that our next step is to find the work ratio. Okay, for work ratio we must be familiar from the to find the work ratio you must know the entropy S at the state point 1. So that is impossible to calculate it directly. We will follow some rules. So a simple TS diagram of the Carnot cycle is just like this. Okay, so isothermal expansion, isotropic expansion, then compressions, isotropic compressions again. So the cycle moves. But to find the entropy at this point, we imagine an imaginary point here. So we extended the pressure line at P2 such that the entropy, the constant isothermal line and the pressure line coincide or connect at the point A. So this whole line basically represent constant pressure, that is 1 bar, and the entropy at this point is unknown, and entropy at this point can be calculated because at this point we have the pressure that is 1 bar, but at this point we don't have any kind of information like the pressure of P1 is unknown and the entropy of S1 is also unknown because S2 and S1 is equal and we have no clue how to find it. So that's why we have extended this isothermal line and extended this constant pressure line further, so we get another extra point with the help of which we can find this S1. Okay, I think you understand my point of view. Now for this process 4 to 1 follow 4 up to 1 follow the isothermal process because it is perpendicular to this T, so it follows the isothermal process. So temperature is throughout is constant. So we know that change in entropy is equal to change in heat divided by temperature. Okay, so we already familiar with the definition of the entropy. But during isothermal process, because from 4 to 1 we have isothermal process. For isothermal process, the first law of thermodynamics says that change in heat is change in internal energy plus change in pressure, volume. Okay. Now this entropy is 0 because temperature is constant throughout, so no change in entropy will take place. So the change in heat, that is a change in pressure and this volume. So we also familiar with the equation PV is equal to RT. So in terms of V we can write V is equal to RT divided by P. So put this TQ is equal to RT by P into Tp. So apply the integrations. These are RT are constant. These will be come out from the integration sign. So it become change in Q, and this will be equal to RT and ln P2 divided by P1. So heat transfers in, so this is the final formula that is used, heat transfer or heat input to the system when the system of the process work under isothermal process, reversible isothermal process. So we can put this formula into the definitions of the entropy. So you get that is del S is equal to 1 over T, so T is here, so 1 by T multiply RT into ln P2 divided by P1. So this T will be cancelled with this T, and change in entropy is so from this point 4 up to A. So the pressure point will also vary in this case. So the points are SA up to S4. So entropy at SA is higher than S4. So you will got equal to R ln. So what are the pressures? So you at P4, and what are the higher pressure? That is P4, and at this point what are the pressure? That is 1 bar. Okay, so P4 by P2. So P2 and P1 are one of the same thing. So SA minus S4 is equal to R ln. So what are P4? What are the pressure? That is 210 divided by 1 is not an issue to write or not, but we must consider there is 1 at the denominator always. So this SA minus S4 is equal to R. What are the R values? So the R value is 0.287, that is constant for gas for air. So while calculating the with ln 210, you will got that will be 0.287, and then ln 210, and the final result will look like 1 point. So the final so the answer that got is 1.535. so its entropy change is 1.535 kilojoule per kg. Now next step is to find the entropy S1. So now we have, if we move from process SA to S2 on a constant pressure line, then what will be change in entropy? I have already made a video on expressions for entropy change when there is an ideal case and reversible process. So before coming to this example 5.2, you must read that, and the link of that video is in the description. So change in entropy, I'm just writing the final equations of that video. So the change in entropy is equal to change in constant pressure. So I'm talking about constant pressure, so it's a constant line. Here is the this whole line represents that the pressure is 1 bar. Okay, so the entropy will be Cp ln T1 divided by T2 minus R ln P2 divided by P1. But remember, so the pressure is constant throughout this process, so it will be 0. So your change in entropy is equal to Cp ln T1 divided by T2. Okay, so what is this change in entropy? That is SA minus and S2. So what is S2? S2 is nothing but that is equal to S1. So here you can write S1 also. So SA minus S1, and that is Cp. Cp value is 1.287 1.005 ln. What is T1? T1 is 1073 divided by 288. Okay, so this SA minus S1 I am writing here. So SA minus S1 is equal to, I will open the calculator to find what value will come. So I am solving this calculations. So 1.05, next is the ln, that is 1073 divided by 288, so you got 1.321. So 1.321 kilojoule, so it's a kilojoule per kg. Okay, it's also kilojoule. Now we have S1, so we have two unknown and two equations, so we can easily calculate from this equation 1 and equation 2 the value of entropy S1. So this SA minus S4 into minus SA minus S1 is equal to, so SA minus S4 value is 1.53, 1.535 minus 1.321. So it will give you the value. The value will be 0.214. You can also use calculator as well, kilojoule per kg. Okay, so here SA minus S4, this will be SA, so this minus will go plus S1, so this will be cancelled out with this A, so it will give you the results here is 0.21. so this so entropy at S1, so you got S1 minus, so this is a minus sign, S4 is equal to 0.21 kilojoule per kg, kilo. Okay. But you remember entropy at, and this is the entropy difference from S1 to S4. So by finding this change in entropy up to S4 to S1, change in entropy is now easily determined. So because as I previously told you that that the state point 1 there is no S1 or P1 value given, that's why we extended it further and that it intersect with the pressure lines P1 bar, so that we obtain the state point with the help of which we find we can approach to the again reverse back to the state point 1. So its entropy difference is now easily calculated, that is S1 minus S4. So change in temperatures, again the change in temperature is T1 minus T2, and that is 1073 minus 288. So if you come to this graph, so this temperature, so this entropy difference multiplied by this temperature difference will give you the net work output that is come inside this rectangle. So this work output, you can say this is the net work output. So the net work output is difference of the temperature 1073 minus 288 and change in entropy from state 4 to 1, that is 0.21. So when you multiply that, you will get the result, that is 168 kilojoule per kg. Okay. Sorry, there is no K. So you will get 168 kilojoule per kg. So the net work output is 168 kilojoule per kg. If you look at this diagram again, there are work done occurs during every expansion process. There is work output. So from 4 to 1, this is a expansion process, and 1 to 2 is again expansion process, because in this entropy drop or isothermal expansion, entropy drop occurs but temperature remains constant, but in this entropy is constant but work output is obtained and entropy is the same. So now we will calculate from line 4 to 1, or you can say from process 4 to 1. So from process 4 to 1, it's isothermal process. For isothermal process, the work done is equal to heat supplied. So the amount that you supplied, the heat will be converted into work done. It's very simple. I'm talking about 4 to 1 process. So the heat supplied in this case, whatever. So you know that heat supplied is equal to change in heat. When there is a change in heat, it equal to S and T. So in this case, isothermal process temperature is constant, but change in entropy is taken place. So this change in heat is basically equal to the process change, that is from S4 minus S1 into T. So here I can write the formula. This del Q is equal to, for isothermal process 4 to 1 is S4 minus S1 into temperature. So temperature is higher temperature because it's from process line 4 to 1. Now just enter the value, and it's quite simple. So this S4 minus S1 that we have previously calculated, that is here S4 minus S1. So here if you see that there is a minus sign, that show that the minus sign just only show that the work is done by the expansion due to the expense of the additions of heat supply. So we have no concern about that, but if you can write, you can write the minus sign as well. I'm just writing direct its magnitude, but the minus sign just give you a message for you. Okay, so that is its value is 0.21. So 0.21 multiplied by temperature, that is what, 73. So the work output from process 4 to 1 is, well, after calculations, its calculation is very simple, and that's why I'm not showing it on the calculator. That is 2296 kilojoule per kg. Okay, so this much work output is obtained when the process follow from process from line 4 to 1. Now there is another expansions occur, that is from 1 to 2. So this expansion is called isentropic expansion there, and it also given the work output. So we will calculate the work output for the process. So for process 1 to 2, and that is isentropic process. So in this case, so you know that when there is a, so what is first law of thermodynamics say, that is U plus work done. So in this case internal energy is so in isentropic process heat supplied is equal to internal energy plus work done. But in this case in isentropic it's also called adiabatic, but no heat supplied or rejected. So the work done that is occur in the expense of internal energy. So this internal energy is further equal to CV into temperature difference, and the temperature difference is T1 minus T2. So these are the temperature difference. So that is for process 1 to 2, the work done is, so the work output you can obtain. So the CV value for the air is 0.718 and its temperature difference is 1073 minus 288. If you put, after putting the values of the specified quantity, you will get the value of the work output from the process 1 to 2, that is 563.6 kilojoule per kg. So this is the work that is obtained from the process 1 to 2. Now the gross work output, For gross work output, you have to calculate the total work that you obtain from the process line 4 to 1 and 1 to 2. In this we have isothermal expansions, and here is the isentropic expansion. So work 4 to 1 plus work 1 to 2. So just add this and this value, you will got 793.2 kilojoule per kg. Okay, this is the gross work output. If I write in short, that is GWO, gross work output. In the statement example 5.2, if you can see, we have to find the work ratio. So how you will find the work ratio? It's very simple. So the work ratio is equal to net work, means to say that how much work has been performed and how much total work. So the gross work output. The net work is actually the useful work that a system can give you, and it is in the gross work output. So the net work is 168 and the gross work is 793.2. So by doing these calculations, its value come around 0.212. So here work ratio you will get 0.212 by putting the values of the network. Network is determined from the graph directly. So the product of TA and S will give you the work. This is the network that we have previously determined. So just we have taken this value and put in these equations of formula, and you got this work ratio. Thank you so much for watching. I hope it was a lengthy example 5.2. In futures I will make some more interesting videos related to thermodynamics, examples and problems. Maybe that will sound more interesting for you. Thank you so much.